Welcome. So, we want to understand solutions to the diffusion equation a little bit better, so that we can discuss about what happens in the spinodal region and what type of modifications has to be done to the classical diffusion equation. To do that, we are going to do a little bit of algebra today. It is very simple. Let me go through the steps. We will start with the so called fixed second law. Okay. So, that is a partial differential equation, and the equation looks like this: dou C by dou T is equal to d del squared C. Let me simplify it. Let me take it in one dimensions. So, one dimensions, it is dou C by dou T equal to d del squared C by del x squared. Okay. So, I am interested in looking at solutions for this equation, which are of this type: C minus C naught is equal to some A times beta t exponential I beta x. Okay, what does this mean? This means that I am going to have, so what is exponential I beta x? It is nothing but cosines and sines, right. So, this is basically things like this, right. Exponential I beta x is nothing but cos beta x plus I sin beta x. Okay. So, cosines and sines, this is a shorthand notation to write them. What does cosine and sine mean, and what does the beta represent? Beta represent basically the 1 by wavelength. So, this is the wavelength, and beta is basically related to inverse of this wavelength, right. You can have something which, for example, can have like this, or which can have like this, or even you might have something which is like that. Okay. So, that is basically captured in this, and this is position. So, as a function of position, we are saying that the composition basically has sinusoidal changes with position. Okay. Now, this C naught is there because when I have, suppose without C naught I can have, and when I have these derivatives, any constant that I add will drop off. So, I have put this. And physically what this means is that these compositional variations that I am talking about is about some average C naught. Okay. The C, the composition that I am talking about is some average C naught. So, that is what physically this means. Okay. Now, the amplitude of this wave is given by the A, that is basically the amplitude of this wave, because I can have the same wavelength, but I can have a wave like that, for example. So, this is captured by A. A is a function of time, and it could be different for different wavelengths. Okay. So, that is what we are saying, but A is not a function of position. Please remember, this exponential part is only the position of function, this amplitude is only a function of time. All that we are saying is that for different wavelengths, this A value could be different, but that does not make it any position dependent term. Okay. So, this is very important. So, I am going to consider a solution of this type. Okay. Let us assume that this equation has a solution like this. Then what happens? So, I need to know what this A is, what this beta is. So, let us substitute it here and see what happens. Okay. So, instead of C, so I am going to add C naught plus this I am going to put here. Dou C by dou T, this is the derivative only on time. So, this is the only quantity which has time dependence. So, this d by dt is going to act only on that. So, I am going to get, and because it is only dependent on time, there is no partial derivative anymore. So, it becomes dA by dt, where A is a function of beta and t, times exponential I beta x. So, this is what you get by substituting this expression here, is equal to, when I substitute this part here, then what happens? Again C naught will go away, that is a constant. Two derivatives, that is going to act on this. It is not going to act on this because this is anyway not position dependent. So, A of beta t is going to stay outside, and then the del squared is going to act on this with d, that diffusivity is also staying outside. The del squared, when it is acting on this, dou by dou x acting on it will give you an I beta, and the next dou by dou x acting on it will give you another I beta. So, you will have I squared beta squared, I squared is minus. So, let me have a minus sign here and beta squared, right, and then I will have exponential I beta x, because exponential I beta x you differentiate. So, it will give you exponential. Now, this exponential goes away. So, you end up with an ordinary differential equation which says that dA by dt is equal to minus d beta squared A. This is very easy to solve. So, we can solve that equation. So, let us see how that solution turns out. So, I have dA by dt is equal to minus d beta squared A. So, let me dA by A is equal to minus d beta squared t. What is this? Logarithm of A is equal to some dt. So, d beta squared t plus some constant, right, some plus some constant, let us call it some k. So, if you now do exponentiation, you will get A is equal to some exponential minus d beta squared t and exponential k. So, that is a constant. So, let me call that constant as some A naught, and A naught is nothing but something that you evaluate at time t equal to 0. So, that is a constant, right. So, we get this as the solution for the equation. So, where did we start? We started with the diffusion equation, dou c by dou t is d del squared c by del x squared. We assumed a solution of this type. Okay. So, the amplitude had some time dependence and the solution itself was sinusoidal. If you do that, then the rate of change of amplitude you can solve for. So, basically the change in amplitude is exponential in terms of b squared. Now, if d is positive and if d is negative, what happens is the question. That is what we will look up in the next part of the lecture and try to understand what happens in the case of classical diffusion equation. And you can see if d becomes negative, then this negative sign is going to go away. So, the amplitude is going to, and beta squared is always positive, time is always positive, and then you are going to have something strange that is going to happen here. So, which is what we will discuss in the next lecture. So, for now we have taken the fixed second law, the partial differential equation for one dimensional diffusion. We assumed some sinusoidal solution, and from that we derived an expression for the time dependent amplitude of the sinusoidal fluctuations. So, what happens to them is part of our next discussion. We will take it up and we will try to see what happens in the traditional case where the growth is after nucleation, and what happens if there is some instability like spinodal to this solution, and that is where we will start our discussion next. Thank you.